Hello, this is my bonus presentation for my bonus project for this XFLR5 assignment. So first thing you do is you open up the application and you have to load in your Clark Y um, document, but it has to be ordered the right way. So from like the leading edge to the trailing edge. Okay, so you load that in and you'll see this around here, and it'll also show another one here, but you can just hide that. So, and then you go over to here and you go to XFoil Direct Analysis. And I've already kind of done it here, so I'm just going to walk you through the steps here. So you have to, for this project, you start at an angle attack of -5 to 20 in increments of 1. Okay, and then you have to go up to Analysis to find an analysis. And we keep it at type 1 for this experiment, and for this project is a Reynolds number of 1 million. Yeah, 1 million. And pretty much everything's good here. So then you press OK, and then you go to and you press Analyze, and it'll bring up just one line. It'll bring up just one line with all the plots and that and the graphs for you. And so you go to this, like you go to each graph, and the ones we need are CL and alpha, CL versus CD, and where's the last one? CL over CD versus alpha. And you get those plots. You press A to get back to the whole screen. So then after you get those, you right click, go to current graph and go to export it, and it'll bring you to like one of these documents where you can go into Excel and organize the data. Oh, sorry, like one of these, like an Excel document where you can put them in and organize them. So then after that's just a regular airfoil. Now you want to do a full wing. So to do that, you have to go to Analysis, Batch Analysis, which is basically just over like a lot of Reynolds numbers. So mine, I did a min of 100,000 to 1,100,000 in increments of 10. And then you do Analyze. It takes a while, so that's why I still have this up, so we don't have to wait here. And then it'll give you all these lines to use. And then to go to the plane, sorry, to go to the plane, you go to File, Wing, and Plane Design. And I'm already doing it here. So basically, what you get here is you get a full wing, or you get a plane to show up. So, but you only need the wing. So here, let me go to here. This is the current plane right here. This is what pops up. You'll go to plane and define a plane, then you'll have to make what you want to do your test on. And right now we're only doing test on the wings, but you could do the whole plane with the biplane and the elevator. Save. Okay. See, like it'll show a little tail back there, and you can do your experiment. You can do your keep saying experiments. You can do your calculations with that. But right now we only need the wing. So then for the main wing, to get it to a certain aspect ratio, you go to define, and then you have to kind of mess around. I kept mine at 2 right here, and then I just messed around with the chord lengths, and you'll see the AR over here. So right now it's at 8, which is good. For 4, I think you would do like 1 and 1, and you get 4. So it's just kind of just change it like that. Okay, and then you click save, save, perfect. And then you go over here, and it should be 5, 20. The same thing from -5 to 20 to 1. Click analyze, and it's really quick. And so then you click all these to see this stuff back here. This is for aspect ratio of 8. And so you can also animate it to watch it go through the whole cycle here, for changing the angle of attack. Yep. All right. So then after you get that, to get the values you need, you will go to here, and this is still the same graphs. You just do the same thing, you export them to an Excel file, and then you can organize them for later. And then for this one, you want to get this graph here. And to do that, you want to do it at a 7-degree angle of attack, and you'll get the graph sort of like this. You do one for induced drag versus the wingspan. And then you would also want the induced angle of attack. So you would right click, go to current graph, define graph settings, and then induced angle. You get a graph like this. So then after you export all your graph values to Excel, you'll organize them into said like for CL versus alpha, and this is for the airfoil, this is for aspect ratio, all the aspect ratios, and you organize them, and you get them into a graph, CL versus alpha. Now for this one, we need to find the slope. So what I did is I only used from 5 to 5, for negative 5 to 5, and only use those values to find the slope, or not the slope, the lift curve slope for each one, which would be down here. And you add a trend line. You'll add a trend line in. But if you do it right now, it won't let you, or like it won't be solid because it's not linear. So you won't get a good accurate reading. Anyways, so yeah, you get that down here for each one, and then you need to find the max CL in this plot for each one, and so that you just do equal max of this, and then you need to find the corresponding alpha, and I'll get to that later. And then the next part is you need to find the max CL CD, CL over CD, and the corresponding alpha. It's the same process. You get this graph too. And then the zero lift drag. Here it is. So for the zero lift drag, or the zero lift drag coefficient, you need to find this point where it crosses the x-axis for where CD is 0. So where the drag coefficient is 0. So to do that, I did equals intercept for these two and then these two, and then it would give you the point right here where it crosses the x-axis, and you did that for every single one. Okay, and then next, then you plot your induced drag and induced angle of attack for each one at 7 degrees at the 7 degrees angle of attack, and you'll get graphs like this. And then the last part is all this stuff down here. So basically, you need to find the induced drag coefficient, the induced angle of attack. I did in both degree and radian, and then the downwash velocity for all the aspect ratio ones you did. And so basically, you use certain formulas. So basically, to find the induced drag coefficient and all these values, you use these 3 formulas here. So induced drag is CL at 7 degrees squared over pi times the efficiency times aspect ratio. And induced angle attack is the same thing, but CL isn't squared. And then to find the downwash velocity, you just multiply tan by this value. Or you do tan of this value times the velocity, which the velocity for every single one has been 10. Or the free stream velocity, sorry. Not this one. Here. So to do this, I kind of typed in this formula here, found the one at 7, and then did it divided by pi times, the efficiency for this one was 0.92, and then times 4, which is the aspect ratio. And you kind of just did that for the same thing for each different E, and the only thing changing really is or the things are changing are this, that, and that. And then to find the induced angle tag, you use that same formula, and then to change that into degrees, you do, sorry, you 180 over pi times that, change them into degrees, and then to do the downwash velocity, you would use the radians induced angle of attack, so the tan of that, and then times the free stream velocity, which was 10 in every situation. So then you come over here, organize it all. Here's all the plots and data and charts. Your lip curve slope, max CL and angle of attack, max CL over CD, corresponding alpha. And yep, and that's how you do this project for the XFLR5.